The last session of the afternoon, I'm going to mix it up a little bit as well. We're going to split the presentation between myself and Andrew here, who's my postdoc. He'll step up towards the end. So full disclaimer from the beginning, I'm a professor of machine learning at Manchester, so anything I learnt or know about systems and architectures and ARM, I learnt from this guy, Mikkel, who's over there somewhere. You can blame him. Charles Reynolds is also somewhere around here. There he is. So we're presenting some results from our most recent project with EPSRC Lambda. So the short story of the presentation is that we have a new machine learning training method for training groups of deep neural networks. And we train them as a committee. So instead of just having one, we have a bunch. And when we send predictions to them, when we send requests to them, they all respond and we aggregate their results. So an ensemble approach. The metaphor that we use in this work is that we're trying to get this committee to talk to each other, to work together to solve the problem a little bit better. And what this all results in ultimately is minimized communication overhead during a training process, and it can be entirely distributed, increased robustness to failure of computational nodes, and sometimes we get an improved accuracy. And all of these things kind of lead us to believe that maybe this sort of algorithm, which is in progress, suits IoT and edge devices. So that's hence why I'm kind of here. I'm also, so I'm part-time actually at Manchester, and I'm part-time at ARM Research. So if you want to tell me all your secrets, do go ahead. I've signed the NDAs already. So everyone knows what a neural network is these days. Seems to be the most popular thing ever. You take your big old neural network, you stick images or things through it, and it predicts this is a frog, perhaps. And this is where the great deep learning gold rush began a few years ago. Every company in the world trying to get on this bandwagon. If you can deploy this technology horizontally across lots of different domains, you can make a lot of money. But you're paying for this. As you make these models deeper and deeper and deeper, you have more and more computation, hence why we're all here. So more computations come from more layers. Each layer in a big neural network is roughly a big old matrix multiply. With every additional layer, you get a new layer of parameters. So in this prototypical example I've got here, if we had a neural net with 1,000 nodes per layer, we bring this up to, say, 20 layers, and we've got 20 million parameters to deal with. And this is a toy example. The modern neural networks like VGG and other things like that, they're up into the hundreds of millions or billions of parameters now. So this is a problem. An alternative approach to working with a great big neural network is to train a group of them. So if we train this committee or ensemble of networks and we aggregate their responses to a single question, then we can reduce the amount of computation. But we pay for it in other ways. We usually have them seeing the same, having them see different data such that we can make them form different hypotheses about the underlying problem. But what we get from this is a much reduced amount of parameters. If we effectively cut the network up into 5 pieces, we get far less parameters. And this would be really advantageous if we're going to deploy this on small devices. So this balance between having one great big network and lots of little ones is the focus of the project, trying to find the sweet spot somewhere in between the two. There are advantages to this big one. It will have more capacity. But there are advantages to these little ones as well, in that they will be easier to learn, there will be much less computations, and finding that sweet spot is our objective. This all stems from a theory that's reasonably well known within machine learning. If we take a committee of these predictors, the accuracy of the committee can actually be expressed in 2 terms. The average accuracy of each module within the network, each of these 5 modules, minus the correlations between them. So what this means is that if we were to make these correlations such that they cancel each other out, such that they compensate for each other, then we can make the committee outperform the average. And if we can do that in just the right sort of way, we get an advantage from having this committee. It's kind of like a parliament voting and being worth more than the sum of its parts. But how exactly we do that, that's the focus of this project we've been working on. We have a methodology where all the networks see exactly the same data. We're expanding this to deal with different data in due course, but we work with a particular novel loss function, a novel training method for the networks. So I haven't put any details on here, but you can catch me afterwards if you want to. The loss function specifies really the objective for the networks to pursue, and we have a loss function specified as the individual losses plus correlations between them. So we try to minimize both these terms. And we have this parameter, lambda, in there. So when this lambda parameter is set in a particular way, it determines the degree of coupling between these modules, which I remind you can be distributed on any device we want. So when we have lambda set down to 0, then backprop is just done completely independently for each one of these modules, exactly as if the others didn't exist. If we bring that lambda parameter up in the loss function, first of all, of course, if you had them all training independently, they would all turn out identical. If we bring that lambda parameter up and train them as one giant system, then you would potentially get better performance, but potentially overfit to the training data as well. And it's finding the sweet spot somewhere in between. If we find that sweet spot, we should be able to get better performance in some sort of way. So presenting just some preliminary results here, we use this very classic data set that's known in the machine learning community, the MNIST handwritten digit data. So here it's just recognize handwritten digits of various shapes, 60,000 examples, training and testing, and we're going to use 20 separate neural networks and train them in this way. What we're going to compare first is if we have this set of completely independent networks versus one great big system all coupled together, all working together. So this is the performance we get out of them. So if we get these networks to completely ignore each other during training, then we get about 95% accuracy, which is reasonable. But if we get them to work together, coupling them up completely together, then we get, say, 97, 98% accuracy. Now, we might think, what lies in between these two? What is the sweet spot somewhere in between? And the initial hypothesis that we had was that some tuning of this parameter would give us a higher accuracy somewhere in between. And it turns out quite a lot of the time, it doesn't. It just kind of decreases as we get further down towards lambda 0. But there turns out to be another advantage to this sweet spot in between, which I can talk about now. So if we imagine a scenario relevant to ARM, we might have power-constrained devices. If we had something like a nice mobile phone with a large amount of battery, a large amount of power available to it, then if we want to do predictions about what's in the environment, we could afford to use quite a complex machine learning predictor, evaluate inference time quite a lot. If we want to reduce our power consumption, we might want to run a cut-down version of that model, a less power-hungry method. And we want to balance in between these two. So there are solutions to this. We could store one model for each one of these 4 scenarios, and we could compress the models down or quantize the weights in these different scenarios that we saw in the last talk. Or we could maybe take one big model and cut portions out of it, maybe partial evaluations through the network. But it's all linked up together. So this is an alternative scenario that might work. We could just have multiple networks available to us, and depending on how much power is available, we can just switch some of them off, just not use all of them. When we have all the power available, we use all 5 or all 20 or however many we have. When we're really power constrained, just use a couple. So this is our scenario. We're going to have 20 networks all trained together. And when we've got a lot of battery life, we're going to say use all 20. When we're down at 1 bar here, we're just going to use 5, chosen randomly, all the others switched off. We can just pick those ones and see what the performance is. And the first scenario we're going to look at is, what would the performance be if we just trained them all completely independently? And the results would be this. So if we trained 20 and evaluated them all together, 20 modules, trained them completely separately, we get pretty good performance, 95% accuracy. And as we knock them out, as we use less and less, we maintain our accuracy, which is good. And we only start really losing accuracy down here. But let's imagine what would happen if we built a system where we coupled everything together. So that opposite end of the spectrum. We build one great big model that can really couple all the parameters together and work together. Over on the right-hand side, remember, we have all 20 networks working together. So let's do that. And up here, we see the orange line is above the blue line, so up at 98% accuracy. So when all 20 work together, we get 98% accuracy. But as we knock those networks out, they've become dependent on each other. So as we knock them out, the performance degrades very rapidly. What we would like is some sweet spot in between, where we both have the very high accuracy when we have all 20 networks available to us, but maintain this robustness from right to left. And that turns out to be this point in between. When we have lambda set to some appropriate value in the middle, we can knock these networks out, and right up until we've knocked out something like 14 or 15 of our networks, and the system is still performing better than the blue line. So this same sort of scenario, this is systematically removing networks, but the same sort of scenario you can imagine would apply in an IoT or edge device scenario. If we've got a number of distributed models training and trying to predict, say, what the weather's going to be like later on today, but some of them randomly fail with some fixed probability. What's quite interesting is we have the exact same performance curves here. So just probabilistically dropping these things out has this same resilience to failure. And so when we train the system to all work together, we get this resilience to nodes being dropped out, but we still maintain the accuracy. And we can maintain dominance above the other systems right up until we get 65% of our computational nodes disappearing. And so this is obviously a point where we think potential collaborations with ARM could come in, deploying this across a number of devices. So now, as I said, to mix things up a little bit, Andrew's going to come up and tell you a little bit about the distributed training scheme we have, which will be here. Thank you.
So I'm going to tell you something about how this training procedure for modular ensembles of neural networks works. In particular, I'm going to focus on how this might work in a distributed computing setting. So we're going to take each constituent neural network of our modular ensemble and place it onto a computational node, potentially ARM-based. In this diagram, on the left-hand side, each node contains a neural network. And during training, each of these is going to see some data, such as this image from the MNIST dataset. Each network will then produce a prediction or classification on that data. And then, in contrast to some other distributed training algorithms that require the transmission of network weights or of data, our training procedure for modular ensembles requires only the transmission of predictions on that data, which is going to be much, much smaller. So again, each node here contains a neural network, produces a prediction, and they forward their predictions to some central node, which is going to aggregate those predictions and produce some ensemble prediction. Leaving some details aside, you can think of this as just taking an arithmetic mean, some average prediction. This average prediction is then sent back out to the computational nodes, and again, leaving details aside, this average prediction is used within the backpropagation stage of these neural networks where the learning actually happens. For some numbers, our training procedure requires the transmission of an amount of data that's proportional to the batch size of the data during training, and if we're doing classification, also proportional to the number of classes. So for typical values of these two, you're talking 4 kilobytes transmitted, sent and received by each node per iteration of the training procedure. If we compare this to one of these alternative approaches where we transmit the weights themselves, for the experiment you saw a few slides back on robustness, this would be more like 600 kilobytes of data. And there are tricks you can use to reduce that amount, such as using your knowledge of the distribution of the weights and do some compression. But ultimately, if you're transmitting weights, the amount of data sent is going to grow with the complexity of the network. So if we were to place a modern, state-of-the-art big convolutional network on each node, this number here for transmitting weights could easily be in the tens or hundreds of megabytes, whereas our approach, the amount of communication does not scale with the size of the networks, so we'd still be in the kilobytes. So this kind of setup may not be ideal because we have a central node here that's receiving data from every computational node at the same time, and we may have very many of these. So obvious choice is to structure our communication in some way. So in this illustration, we've simply laid out our nodes into a tree, and it's exactly the same as before. So each node contains a neural network. They all see some data during training. They each produce a prediction, a network output. This root node over here is going to compute an ensemble prediction, an average. And again, thinking of this as just a simple arithmetic mean, we can compute this hierarchically as the data is passed up the tree. So for example, this node at the top is going to compute the average of its own prediction, the 2 predictions it receives, and then it's going to forward that on up towards the root. And once the average prediction is computed, it's propagated back down the tree. Again, as before, the average prediction is used during this backpropagation phase inside each node. So as I've alluded to, the backpropagation, the machine learning, if you like, is self-contained within each node. What this means in practice is that your deep learning framework that's running on one of these doesn't need to know about the rest of this system. And in fact, it doesn't matter for our purposes, for our training algorithm. It doesn't matter if you're running different deep learning software on each node. So in this illustration, we have some nodes running Caffe, PyTorch, TensorFlow. Maybe these two are running different versions of the same software, and it's all fine. For similar reasons, it doesn't matter for our purposes if these nodes consist of different hardware. So here we have an example of an ensemble, a modular ensemble, being trained in parallel. Up here we have maybe 3 mobile devices. It looks here like we've got a researcher at Facebook and Google, respectively, CPU, GPU. We've got a Newton enthusiast over here who's somehow managed to install PyTorch, who is happy to help. The summary here is that our training procedure is amenable to parallelization with very small communication overheads, and that we can take advantage of very large-scale systems and potentially massively heterogeneous systems. We are very much looking to exploit large-scale machines and large-scale clusters. We'd really like to do some experiments with the training and inference on extremely large-scale ensembles. One potential platform for this is the Spinnaker machine at Manchester. It currently stands at 500,000 ARM cores. I believe soon we'll have 1 million ARM cores. And we are looking for other platforms for this. On that note, I think we're ready to summarize.
Yep, I won't take up any more time. You can see the conclusions on the slide, and we're looking for collaborators. So thank you very much.
So we have some time for questions now.
I wonder wonder about how the accuracy maintenance changes if you evaluate it on different data sets. So switching from MNIST to any other network. Have you some numbers to that?
Not dependent on the data set.
It's not?
No, we've tried lots of other data sets. This is a generic methodology for any data set you feel like, not even restricted to classification problems. Other classes of problem as well.
Yeah, even if you scale up to bigger models, that's still...
Yeah, we've tried this with convolutional networks and ResNets. These sort of principles apply.
Okay.
Yeah.
Thanks.
Hello, Jose Cano, University of Glasgow. Here. Yeah.
Right in the light,
So,
okay.
yeah. So I think it's a nice approach, what you presented. So can you give us a real example of how this would translate? Imagine we have a big network, BGG19, for example. How this actually translates in small networks, and can you assume heterogeneity among these networks in order to provide the capacity of the big network, the initial network? So can you give us an example, a real example?
I don't really understand the question, sorry.
Yeah, you have a big network, right?
Yeah.
That you want to have smaller ones, let's say 5 networks. So obviously, how is this BGG19 network translated into smaller ones? Which networks can you actually use? And can you use heterogeneous
Sure, I understand.
smaller networks?
Right. So we're not proposing a methodology where we take one big one and then a method to break it up.
Right.
We're more saying take whatever computational limits you have on one device, build a network to fill that as far as you feel like, and then you can have 2 devices, 3 devices, n devices physically separated, and they can train. So if you can fit your VGG net on that device, then fine. If you have to compromise and make it smaller, then you can take advantage of the fact that you've got the system working for you.
So making it smaller means that you can prune the network, for example?
You could do that, yes?
Right. Okay, I see.
Yeah, this is a meta-learning technique. So any of the methods that we've seen today, the quantizing and so on, could be used in concert with this. And in fact, we haven't mentioned it, but nothing we've said here is specific to neural networks. All of this distributed training procedure could apply to any other class of machine learning model you felt like playing with. It's a meta-learning method.
And do you have any numbers of a real baseline example that you use to apply this methodology?
We can show you afterwards. We don't have anything on the screen, yeah.
Right, thank you.
So one.
I enjoyed your talk. Thanks so much. A question about quantifying uncertainty out of your neural network predictions. Is this provide a framework for assessing, for example, prediction intervals around, or getting a distribution on your predictions?
It's a good question. Do you want to answer it?
Thank you.
In general, I'm curious about how you quantify,
quantifying uncertainty.
Quantifying uncertainty.
General, yeah.
I think I can say something.
Yeah.
We've not thought about that. Now, in the case, so we have this lambda parameter, right, that determines the degree to which your modules disagree. In the case that we set that parameter to 1, we may have an approach for quantifying uncertainty because there's a surprising relationship between what we've described and dropout. And dropout is often used at inference time to quantify uncertainty. So potentially, yeah.
You talked about correlation. So how do you measure correlation between the networks?
Information theoretic. So I can show you an equation later on, but we haven't in fact put out the publication on this yet, so okay. I didn't want to put any equations up on the screen.
Right. So to measure the correlation, you don't have to communicate the weights or anything, right?
Sorry, what?
To measure the correlation, you don't communicate the weights, right?
I'm sorry, I didn't hear that at all.
To measure the correlation, you don't have to communicate the weights to the end node.
No. Correlations are computed on the individual nodes, and it's an information theoretic formulation of dependency there.
Thank you.
Really great stuff. Have you seen, because you say you try with different data sets,
yeah.
and perhaps different questions, I was wondering, have you seen any correlation of, or any convergence of the number, the lambda tends to relate it to the number of networks that you try to cut the
yeah,
bigger
interestingly, yeah, there is quite a strong dependency. As we add more networks, kind of the optimal value seems to tend towards 1. There is some convergence there. We're still working on the theory. There's all sorts of directions we could take right now. Hence, we'd like some collaborators.
One last question.
I think Javier had one.
For more changing datasets than MNIST, for instance, ImageNet,
Yeah.
if you want to, instead of training a single super large network, you have multiple very small networks.
Yep.
Have you explored how do you split the dataset into multiple small networks? Because probably if you try to learn random image samples of ImageNet into a very, very small network, probably they are not going to learn anything. So maybe if you split, okay,
we don't split data at all.
Okay.
All networks see precisely the same data, but it's the way in which they communicate that determines their differences.
Okay. Thank you.
And I guess this session is over, and let's thank the speakers.